Hey, welcome. In this explainer, we're going to dig into the hidden rules that basically run our entire physical world. Yep, we're talking about measurement, the absolute foundation of physics, science, and, our everyday lives. So let's dive right in.
I mean, it sounds simple, right? But hold on, think about it for a second. For science to work, for global trade to function, my kilogram has to be the exact same as your kilogram, whether you're in Tokyo or Toronto. So, how on earth do we make that happen? That is the big question we're going to tackle today.
All right, here's our game plan. First, we'll nail down what measurement actually is. Then we'll explore the four different scales of information we can get. We'll look at the universal rulebook that keeps everyone on the same page, check out the tools we use, and finally, break everything down into just two basic types of quantities. So let's start at the very beginning. What is measurement? It sounds all technical and complex, but at its heart, it's actually just a really simple act of comparison. And that's pretty much it. Seriously. Every single time you measure how tall you are, or weigh some flour for a recipe, or even just check the time, you're doing this one simple thing. You're comparing something you don't know, like your height, to something you do know, a fixed standard, like a meter. This simple process is what turns our kind of messy world into clear numbers we can actually work with and share. Okay, but here's the thing. Not all measurements are created equal. Depending on what we're measuring, we get different levels of information. And that's where the four scales of measurement come in, with each one getting a little more powerful than the last. We start with the nominal scale, which is really just simple labels. Think hair color, blonde, brunette, redhead. Then we level up to ordinal, where the order actually means something, first, second, third place. Next up is the interval scale, where the gaps between the numbers are consistent and meaningful. And finally, we get to the big one, the ratio scale, the most powerful of all because it has a true absolute zero. Let's break that down a bit more. So you can see how each scale gives us more power. Nominal just puts things in boxes. Ordinal ranks them. The interval scale lets us add and subtract. Think about temperature in Celsius. The difference between 10 and 20 degrees is the same as between 20 and 30. But the ratio scale? Oh, that's the real superstar. Because it has a true zero, meaning none of that thing exists, we can multiply and divide. We can say with total confidence that something is twice as long or has half the mass. And that's why pretty much all of physics happens on the ratio scale. Right, but if we're all going to be measuring things so precisely, we all have to agree on the units. We need a universal rulebook. And for pretty much the entire world, that rulebook is the International System of Units, or as it's better known, the SI system. And this is just so important. Without it, science and global trade would be complete chaos. A standard has to be something anyone can access, and it has to give the same result no matter who's doing the measuring. It's basically the ultimate source of truth for the physical world. Now, you might think the rulebook for the whole universe would be thousands of pages long, but here's the wild part. The entire complex world of physical measurement is built on a surprisingly small foundation. Just seven. Seven base quantities. Think of them like the primary colors of physics. From just these seven, we can describe absolutely everything else. And here they are. You already know the big three, of course, the meter, the kilogram, and the second. The others, like the Kelvin for temperature or the ampere for electric current, might sound a little more technical, but trust me, they're just as fundamental. And here's the really cool part. Every other unit you can possibly think of, from speed to force to energy, is just a combination, a recipe, made from these seven basic ingredients. Okay, so we have the rules, the SI system. That's the theory, but how do we actually apply them in the real world? Well, we need tools. Let's take a look at how we turn these abstract ideas into actual, tangible measurements. This is where the rubber meets the road. We use meter sticks for length, a beam balance for mass, and a stopwatch for time. And all of these tools are calibrated to those super precise SI standards we just talked about. This is also why something like a sundial isn't used for science anymore. I mean, it's cool, but a shadow in one city isn't the same length as a shadow in another. It's not standard, and it's definitely not accurate enough. All right, for our last piece of the puzzle, let's look at all these physical quantities we've been talking about. It turns out every single one falls into one of two very simple categories. Just think of them as building blocks, and the blueprints you make with those blocks. On one side, we have the fundamental quantities. These are our seven SI base units, the absolute basics, like length, mass, and time. You can think of them as our Lego bricks. You can't break them down any further. Then on the other side, we have derived quantities. These are all the cool things you build with the Legos. They're created by combining the fundamental ones with math.
So speed, that's just a length brick divided by a time brick. Area, that's just a length brick multiplied by another length brick. See? Everything that isn't one of those original 7 is just a derived quantity.
So there you have it. We went from a simple act of comparison all the way to the fundamental building blocks of the universe. The big takeaway here is that our standards are always getting better, always evolving to be more precise. We used to define the meter by a physical metal bar locked in a vault. Now it's defined by the speed of light, a true universal constant. Which leaves us with a fun question to chew on. What everyday standard do you think will be the next one to be redefined by a constant of nature? Something to think about. Thanks for tuning in.